Okay, so we are reading this paper. It's like 7 pages or 8 pages, 7 pages, and it will appear in Cider in a couple weeks, I think.
Hmm.
Okay, and let's get started. It's interesting. Uh, it's interesting topic. Cloud specs, cloud hardware evolution through the looking glass. I think this is a pun because um, what was his name? Stonebreaker kept writing OLTB through the looking glass, this through the looking glass, like for the through the looking glass after 40 years, and I think
I mean,
they are
I'm not
making a
sure
pun.
it's really like a pun. Like Viktor was on that second Fruit Looking Glass paper, I believe,
Really? OLTP through the looking glass?
if I'm not mistaken.
Check it out. I'm sharing screen and I don't want to change, but
16 years later, right? Uh, yeah. Um,
okay.
and the yeah.
Looking glass is all you need. People keep titling things like this. Okay, cloud specs. I'll read the abstract you follow up. Public cloud hardware has evolved rapidly, with vendors offering hundreds of instance types, differing in CPU, memory, storage, and networking capabilities. Yeah, it's confusing, right? So
Mhm.
many choices. This paper presents a comprehensive analysis of cloud hardware trends from 2015 to 2025, focusing on AWS and comparing with other clouds and on-prem hardware. While network bandwidth improved per dollar by one order of magnitude, wow. Okay, in 10 years, okay, not so wow, but still one order of magnitude. CPU and DRAM gains are much smaller. Okay. Yeah, I mean, I expected the CPU gains to be smaller because of like the end of Moore's law and stuff. DRAM,
Okay,
huh, okay. DRAM
it's
is okay,
per
it's probably
dollar,
the same reason.
right?
Per dollar, yes,
So it
yes.
doesn't mean that, you get less CPU or same CPU. It just means that, it's not cheaper.
Yeah, yeah. Still, NVMe storage performance has stagnated since 2016. This is even more surprising to me. Maybe not. NVMe. By NVMe, do we mean like SSDs?
NVMe SSDs.
Okay. Okay, then it's a bit surprising. I would have expected. What is storage performance though?
Mhm.
A cross-cloud price comparison shows that smaller providers undercut the big three hyperscalers by up to 5 times for commodity virtual machines. Okay. Our findings reveal shifting bottlenecks and highlight new challenges in designing cost-efficient cloud-native data-intensive systems. That was a hell of a sentence. In designing cost-efficient cloud-native data-intensive systems, which is not saying much. An interactive tool supports further exploration of the evolving instance. Oh, interactive tool. Me likey, but how are you going to show us the interactive tool through the
There,
paper?
there is a URL cloudspecs.fyi.
Okay, we, we will check it. Yep, I see it here. Mm, okay, shift to the, it's your turn.
Yeah. The tool looks like a query. Select star from AWS and it gives you like a big
Hmm.
table.
Okay, hold on. Let me bring this here so I can share when it's time. It's a big table. I was oh, God damn it, interactive using SQL. How is this interactive? I was thinking this would be interactive with you know, uh, with those sliders to show something. Is your idea of interactive SQL? Okay, fine. I should have expected. Let's keep reading.
Well, these are database people who have written this paper,
Yeah,
so.
yeah.
Okay, introduction, right? Shift to the cloud. A growing number of database systems are now deployed on public cloud platforms such as Amazon Web Services, Microsoft Azure, and Google Cloud. In these environments, database systems typically run on virtual machine instances connected via Ethernet. As a result, the system's performance, scalability, and cost are constrained by the available instance types and their associated prices. Cost efficiency versus system architecture.
Aleksey,
Yeah.
are these VMs connected via Ethernet?
Well, kind of, right? Like, it's not going to be your you know, like physical Ethernet plug that you have in your
Yeah.
like computer,
Mm-hmm.
right? These network cards have different connectors, right? Because they're not
Mm-hmm.
like
Mm-hmm.
1 gigabit or
Mm-hmm.
whatnot, right? But like ultimately, it's still network cards, right? And you know,
Yeah,
copper
but
or
Ethernet is pretty
fiber.
much single hop, right?
No,
Why do they have to be like Ethernet is pretty much deployed as star topology and
no.
no, okay.
Where we are. Cost efficiency versus system architecture, right? Um,
Mm-hmm.
okay, so in a cloud, what often matters most is not peak performance, but performance per dollar. This shifts the focus from raw throughput to economic efficiency, making cost a first-class design consideration. For instance, depending on relative pricing of CPU, RAM, SSD
Mm,
storage, and networking, it may or may not be cost-effective to cache data or to that reminds me of the paper we read last time.
yeah. Yeah, yeah, yeah.
To cache data or disaggregate the system onto separate compute, caching, and
I
storage
mean,
layers.
the paper we read last time took a strong stance. It said that it is very much cost effective to cache data. It's cheaper, 3 to 4 times cheaper was
Mhm.
that paper's claim, and this is saying that it may or may not be cost
Yeah.
effective.
Designing cost
That's interesting.
efficient.
What is number 10?
It's a CIRA 2025 paper.
By who? Okay, the 5-minute rule for the cloud
Yeah.
caching in analytic systems. Okay, interesting.
I think the other paper also cited this, no?
Hmm.
Um,
Okay.
Designing cost-efficient cloud systems therefore requires a deep understanding of the cloud hardware landscape, including the range of instance types, storage options, and pricing models offered by cloud providers.
Sure, I very much agree with this. Okay, going back to the Ethernet thing, like, does it mean they have to be in the same LAN or same data center? Can the instances not be across AZs? Does
So
Ethernet constrain us?
what they're trying to say is they're not using, and yes, it's Ethernet, but what they're trying to say is that they're not normally using things like InfiniBand, for example.
Okay.
Right. So,
Hmm.
they have normal switches and whatnot, like, right? So, rack, top of rack switch and blah, blah,
Yeah,
blah. So they build this like a
I see.
FAT3,
Yeah, sure.
cloud, data center like network, right? But not with, probably things like InfiniBand.
Okay.
Mm. And then
Okay.
you can still like run some pretty cool technologies like ROSI, RDMA over
Mm-hmm.
Ethernet.
Mm-hmm.
Right?
Okay. Okay, I'll read this one. A vast multi-dimensional landscape. Cloud providers offer hundreds of virtual machine instance types, with new configurations introduced regularly. As Figure 1 shows, available AWS instances by CPU vendor here and wow. Okay, it's also interesting. More AWS Graviton. It's
Yeah.
becoming more of a thing. AMD is getting a lot more, uh, share, and Intel share is still growing. You know,
Yeah, well, it's the number of instances, right? Not number of actual running, VMs or servers.
what's the difference?
Like different instance type, you know? You can choose
Oh,
right now
instance types. Yes, yes,
between
yes. Okay.
1057
Hmm.
different
Hmm.
instance
Hmm.
configurations, essentially, right? Combinations of
Right, right,
CPU,
right,
RAM, blah, blah, blah.
right. This is instance type proliferation or something, whatever is the word. Okay, got it. But it's a funny graph. Okay. As Figure 1 shows, since 2015, the number of AWS instance types have grown from 52 to 1057. Oh my God, that's like Steve Jobs would not like this. Google Cloud currently offers over 400 instance types, and wow, they are catching up to AWS. Microsoft Azure more than 1,000. Okay, Microsoft Azure caught up in this metric. Instances differ in key dimensions such as CPU type, memory size, network bandwidth, and storage capacity. Hmm, okay, storage capacity. Like cloud storage with disaggregated, I don't know. Like this is becoming more of an interesting thing. All of which impact both performance and cost. Navigating this complex and ever-changing space is a core challenge in cloud system design. Okay, your turn.
Contributions. The goal of this paper is to demystify the cloud hardware landscape by analyzing current cloud offerings and tracking their evolution over the past decade.
Tracing the revolution.
Tracing, yeah, tracing their evolution over the past decade. We focus our analysis on AWS, which is the largest cloud vendor, but also compare with on-premise hardware and other cloud vendors. In addition, we discuss the implications of this evolving hardware ecosystem for data-intensive systems. Given the multidimensional nature of the cloud instance space, any static analysis is inherently limited. To support deeper exploration beyond the paper, we therefore provide an alternative visualization tool that enables cloud system architects to answer specific instance selection questions rigorously. Our tool is available at link.
And it is okay. I'm going to share the uh, I'm going to share this. This is the tool. There's the sequel.
Well, there is a visualize button.
Well, okay.
Maybe the
For,
paper explains how to write more interesting queries that can be visualized. I don't know.
download database DuckDB. Okay, this is over DuckDB. And like 100 entries per page. Of course, it's 1,000, so it's 8 pages or something of this. And how do we check AWS versus others? Oh, select from AWS. Okay. If I say Azure, execute. See, oh God. Microsoft? What do I write?
They actually have some queries. You can select a different query.
Yeah. Column info, available instances per release. Okay.
See,
I guess
now it has a figure.
Yeah. Okay. Okay. I take it back if you know how to write well, if you make if you point your LLM to this and make it write the SQL, change your natural language queries to SQL and paste it here, you could make it work. Otherwise, you will have to figure out like what to write for vendor. Okay, vendor is this. Provider is like, ah, okay. This is figure one.
Yeah.
Network bandwidth per. Okay, this is sort of fun. Yeah, it's sort of fun. Okay, I'll play with this later. Share. Okay, back. Cloud hardware trends, data sources. AWS publishes extensive hardware specifications through several overlapping but incomplete APIs and websites. Ooh, dissing AWS. For example, the describe instances API contains many important hardware specifications, while some instance storage performance data is only available on a web page and prices are available through the price list API. We therefore extended the open source instances vantage.sh data crawler with additional data sources like instance-type.es website that contains instance release dates to produce a curated database combining all information relevant to this paper. This process is fully automatic, and we plan to maintain this database in the future to facilitate tracing the evolution of cloud hardware. We use data as of October 2025. I hope this is not a dataset paper, right? It is not. They are going to interpret this if
Yeah,
we go
yeah.
by the. Okay, I'm more interested in the interpretation. Okay, Alex, your turn. Maybe we read these parts fast and go to the interpretations.
Instance families and slices. AWS allows renting virtual slices of the same physical server. The i3 instance family, for example, is available in the large, extra large, 2 extra large, 4 extra large, and so on sizes. Within a family, the price and hardware generally scale proportionally. For example, 2 extra large costs twice as much as extra large, and also has twice as many CPU cores, DRAM, instance storage capacity, etc. Thus, in most cases, the cost normalized metrics, such as cores per dollar, are exactly equal for all instance slices within one family. Whenever this is not the case, such as network bandwidth, we show the largest slice. For most analysis, it is therefore sufficient to show only the family name i3 rather than the full instance name,
Yeah,
like i3 2 extra large.
yeah.
Instance selection. Okay, because we focus on common database use cases, the main analysis excludes instances with accelerators and FPGAs. And the economics of GPU instances are discussed separately in section 2.5. We also ignore.
I mean, I wanted to. I was hoping the cloud trends was more about these FPGAs and GPUs, but this is more about like AWS boring instances, making more. Maybe that's more practical, but this would be more interesting.
We also ignore instances with shared overcommitted CPUs, such as burstable T and flex instances. This leaves us with 742 relevant instances, or rather instance types, right, across 98 instance families, which differ in terms of CPU, RAM, storage, network capabilities, and pricing. Note that our online database still contains all instances, allowing more detailed analysis of GPUs and accelerators in the future.
Okay, prices. Given how easy the cloud makes switching instances, comparing instance specifications without taking into account their prices is misleading. What does this sentence even say? Like, I'm not any wiser. In most cases, we therefore normalize instance metrics relative to an instance's hourly price. Okay, where are we going? We use prices from the US East 1 region, which is the largest and often also the cheapest region. While AWS offers multiple discount models, we use on-demand prices as the basis of comparison. Spot instance prices are highly variable based on short-term availability fluctuations. The discount rates of savings and reserved instances are broadly similar across instance types. I feel like I'm reading medicine side effect things. So far it's boring.
All they're saying is, they take the public prices, right?
Yeah,
That's the only
yeah. I
prices
mean,
that are available.
right, right. And they are not looking at spot, of course. Uh, this discount rates of savings and reserve borders. Demand prices will therefore merely overestimate the true cost by some factor, but will not distort the overall price structure. Also note that AWS has not decreased on-demand prices for any instance since 2018. Disruptions occur through the introduction of new instance types and the slow obsolescence of older ones. Okay, CPU trends. Okay, I think we are getting to good stuff.
CPU trends, more cores. Just
Yeah.
like the on-premise world, the cloud has seen tremendous growth in multi-core parallelism. The biggest AWS instance, I'm not going to say that name,
Ooh.
has 448 cores. I bet it's a Graviton, right? Um, um, Focusing
Can
on
can we
compute.
see if it is a graviton by the naming convention? Okay. I'll
Um,
search.
uh,
Can you Google?
High memory UCI instances, powered by 9.9 gigahertz, fourth generation Intel Xeon Scalable Sapphire Rapids.
Oh, Intel is still
But
doing
I don't know
good.
if I got the right one. I'm looking at the U7i, and they had that was U7iN.
Okay, no. I think the IN is Intel. I don't know. Maybe I'm
I mean,
making
yeah,
this
I
up.
think I think Graviton will have G in the name,
Yeah.
if I remember it correctly.
Mhm. Let's keep reading. Focusing on compute optimized instances, only the maximum core count increased by one order of magnitude over the past 10 years. Yeah, we have
Mhm.
seen this in the intro. The C4 instance family, introduced in 2015, provides a maximum of 18 cores, while the C7A family, introduced in 2023, features up to 192 cores with instance. However, as we will see, this increase does not translate to higher performance per dollar. Yeah, I mean, more cores, but are you able to use? I don't know.
I mean, you're using them, right? It's just that, like, yeah, I guess in pure like performance benchmarks,
Hmm.
the
Right,
price may be the same, right?
right.
Like the price per unit of actual like compute you get out of that.
Hmm.
More CPU vendors. A second major CPU trend shown in Figure 1 is that Intel is not the only CPU vendor any longer. AMD CPUs, and particularly the ARM-based AWS Graviton CPUs, have become common as well. Indeed, since 2024, more than half of newly released instances use Graviton CPUs. CPU benchmarking. Having dozens of CPU models that differ in terms of their instruction set, architecture, vendor, and CPU generation makes choosing the best instance difficult. Adding to this difficulty is the fact that AWS classifies the degree of parallelism as vCPUs, which, depending on the instance type, represents either hyperthreads for x86 instances or full cores for Graviton instances and 7CA. To compare CPU performance more accurately, we ran three benchmarks. The CPU performance benchmarking suit spec in 2017, in-memory TPC H, scale factor 10 on database system Umbra, and in-memory TPC-C, 25 warehouses on the storage engine Lean Store. And of course, database people. We ran the experiments on the 2x large slices of compute-optimized instances using all available hardware threads.
Okay. CPU cost performance evolution. I think this is what we have been getting at, right?
Yeah.
No increase in terms of the per dollar performance. To see how cost performance evolved over the last 10 years, we normalized the results by the performance and cost of the C4 instance such that higher values indicate better cost performance. Figure 2 shows the results for three multi-threaded benchmarks. For SpecInt, cost performance improves by about 3x over 10 years. A big part of this improvement is due to the introduction of Graviton instances, without which the gain would be closer to 2x. So it improved. It is therefore not surprising that major cloud-native systems such as Snowflake have been switching to Graviton instances. For in-memory database benchmarks, the gains are even lower, ranging from 2x to 2.5x. We speculate that this is because in-memory database performance is strongly affected by memory and cache latency, but leave a detailed microarchitecture analysis for future work. Then why do they say that it is? It says that this does not translate. This is 10x improvement versus 2x, 3x improvement. I see.
That's the figure.
Figure 2. Okay, what do we learn from figure 2?
Graviton is cheap. Yellow line.
Oh, cost per performance. Cost performance relative to zero. Okay. Okay, it improved by 2-3 times, but not 10 times as the number of cores. Well, what do you expect? That's still, that's still good.
Yeah.
And these links, what are these links? They are clickable to queries in the database web page.
Yeah.
That's cool. Yeah, by clicking we see exactly the figure, huh? Opening Google Chrome, a big URL with I think the SQL the state encoded in the URL, and I don't see the figure, but I see. Oh, no, figure is coming because it executed and it created the figure in real time. Nice. Way to write a paper. Okay, Alex, your turn.
On-premise comparison. Historically, Moore's law, more transistors per area and therefore per dollar, and Steinert scaling, higher performance via higher clock frequencies, led to cost-normalized CPU performance doubling roughly every 2 years. Over a decade, this would imply 5 doublings and a cost performance gain of 32x. This raises the question of whether the relative CPU cost performance stagnation is due to higher margins for hyperscalers or due to technological stagnation, the end of Moore's law. To answer this, we analyzed AMD server CPUs from 2017 to 2025. Based on list prices, core counts, and clock frequencies, and published IPC metrics, we observed a similar trend, 1.7x with on-premise AMD server CPUs as within AWS. Thus, it seems that the cost performance stagnation for server CPUs is not cloud-specific, but a general tectonic shift in the technological landscape.
Okay, so they did the same comparison on
Hmm.
real hardware that they get their hands on, and they okay.
Well, again, like I am not that surprised, right? Like,
Hmm.
have you like looked into the machines that they need to use to make this like wafers, right?
Hmm. Hmm.
Uh, what is it like 3 nanometers or whatever? It's like two
Yeah,
nanometer scale at this point, right?
yeah,
Like these machines are massive, right? They run lasers to evaporate
yeah,
metal to produce X-ray that will then like reflect off a bunch of mirrors that then etches stuff, right? It's
yeah,
like X-rays and whatnot. It's like
yeah.
and they cost like a big airplane or something, right?
Yeah, ASML is
Yeah.
producing them, the Dutch company, and
Yeah.
it's
So
like
so
really nice YouTube videos on the technology. Lithography is
and
like
it's
magic.
like so yeah, there is a technological stagnation. We got to the limit of like physics, right?
Yeah.
In trying to shrink those things.
And then, yeah, I mean, right? I mean, hardware had been delivering miracles. It's time for software to deliver the miracles, but we don't know how to use multi-cores. I don't know. Maybe with LLMs, we will write software that's more efficient. Do you
Oh
think
no,
that
oh
that
no,
makes better use of the cores?
oh no.
I don't know. Yeah.
So I was writing something with Claude today, right? And I gave it a task, and it wrote the code that worked. It produced a good result, but it was
Mm,
like running the thing for I don't know 15 20 seconds, right?
mhm,
And then I start looking at the code and whatnot, and like it's just like it's doing stupid, right?
mhm,
Luckily, of course, I just had to tell it that, hey, you're doing stupid. Maybe you should do it the other way and give it a hint on how to do it
mhm.
differently. And, in 2 minutes, it rewrote things and, the same stuff instead of taking like 30 seconds takes, a second or whatnot, right? But, I knew kind of what to look for and where to poke it, right?
Mhm.
In 20 years, we'll have
Yeah.
engineers who don't know what to look for and where to poke.
Yeah. I mean, but we did drop the ball on multi-core. Like software is at fault here. We should be using it better. I mean, what I hear from people is for more effective use, they pin actually one process
Yeah.
to a core. And they say this is more effective than trying to use threads and stuff because like we have so much overhead.
No, they don't pin one process to a core. They pin a process to a set of cores and then manage those cores within the process. That's what you would do for high performance software.
I even saw one process pinned to a core. Uh, I guess more compute heavy process, but that works better than trying to let loose threads on cores.
So like that's literally what we do, right? We tell the OS, hey, don't touch this course, right? So we
Mm,
make the OS not schedule anything on a subset of course. Then we pin our, performance critical process to those cores, and our process itself will manage,
mm.
what work is done on what on the course.
Yeah. Okay, let's keep reading. Main memory, memory capacity. Besides core count, AWS instances also vary greatly in DRAM capacity. The cost normalized DRAM capacity shown in figure 3 exhibits very little improvement over time. Cost normalized. Okay, yeah. The keyword is cost normalized. There is also inflation. Maybe they should have normalized against the inflation. Thanks, Obama. Ay, ay. exhibits very little improvement over time. The only major change was the introduction of an additional group of memory optimized instances with an X prefix in 2016, which offers roughly 3.3 times more gigabyte hours per dollar than the best compute optimized instances. Okay, AWS also offers instances with very large DRAM capacities of up to 32 terabyte. Use 7 Intel, I think, blah, 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 though their capacity per dollar is significantly worse than the X and R instances.
As figure 3
As
shows.
what is X and R? Okay, no, X is the memory one. R is I don't know, and this U is I don't know. Okay, main capacity one, figure 3. That's only figure 3, and let's look at it. Okay, it's all X's, R's, and M's, and C's, and U's.
Mm.
It would be good to know what they stand for. What does U stand for?
Uh,
Oh boy.
we already looked at U7I, right? So these are the
Yeah,
high memory, high CPU count
I
instances.
mean, it looks like X is even more high memory,
Mm.
3 times more. M is medium. What is M? What is
Don't
C?
try to decipher the letters.
I shouldn't.
Mm-mm. I'm pretty sure M is some kind of general compute instance. Yeah, it's like
These naming suck. Ah, humans are supposed to choose this. Okay, let's keep reading. Memory bandwidth.
during the past 10 years, server CPUs transitioned from DDR3 to DDR5 while supporting more memory channels and higher transfer speeds. Just wait a year, we'll transition back to DDR3.
Why do you say that?
Well, I'm kind of joking, but with all the
Hmm.
DDR5 being bought by AI,
Oh yeah, I see. Yeah,
you will run your databases again on DDR3.
yeah. I mean, but right. So I think the biggest trend I could see from these Amazon's announcements at yearly, annual, what is that called? Reinvent is like the biggest gains are from the memory bandwidth. They keep increasing the memory bandwidth. That's the trend in memory design. They want to have bigger bandwidth between CPU and memory, and that's what Graviton's actually focused on. And it looks like Graviton has
Yeah.
better cost performance. So
So so
that
so
seems to be paying off.
so this is the counterpoint to what you're saying, right? So they say
Okay.
that absolute single CPU socket bandwidth increased from 93 gigabits
Mm,
per second to
mm,
492, right? So that's a 5x
mm,
improvement.
mm,
Um, but at the same time, if you remember, well, it's a single
mm,
CPU socket, right? So um,
mm.
but they also said that their core count went up by like 10x or more than
Yeah.
10x, 20x, right? They say 440. I mean, it's
Mhm,
not a single
mhm.
socket system. It's probably like four sockets or whatnot, right?
Uh-huh.
But you do have more cores.
Yeah.
Like the number of cores increased higher than your memory bandwidth. So actually, you may end up right now in a situation where you
Mm.
have less bandwidth per core than before.
Yeah, yeah. Like my question is, where is the culprit? It's software, right? And
Culprit for what?
inside, I mean, these waste, they keep complaining. Oh, this increased 10 times, but this only increased. This increased 5 times, but this only increased 2 times. Where does this wastage go? Is this normal? Maybe it's normal.
No,
I don't know if this is
it's just the
normal or not.
technology, right? It's just that the memory is only 5 times, faster. The CPUs may have 10 times more cores, right? If you make memory 5 times more bandwidth, but the CPU, 10 times more cores, then you end up with half the bandwidth per core. Right, so now you have a fast core that can compute more things,
Hmm.
that has half the bandwidth of that slow core from 10 years ago. Right. I'm
Okay.
kind of doing the napkin math for you, right?
Yeah, yeah,
But
no,
but but this but this notion that the memory bandwidth per core
hmm,
doesn't increase and may even go down is
yeah.
real. And I wonder if we can use their like lovely website to try
Hmm,
to calculate that.
I see. Okay. Okay. On-prem comparison. We again ask the question, how these trends compare with on-prem hardware in terms of capacity? Historical data suggests commodity DRAM prices decreased by roughly 3 times during the past 10 years. On-prem, well, again, badly timed paper, right? The last couple of months. On-prem memory bandwidth per dollar has similarly improved by a factor of 3. Thus, both memory capacity and bandwidth cost improvements in AWS closely track the corresponding developments in the non-cloud server market. Okay.
It's kind of funny. It's a bad timing, right? Um,
Hmm.
we got a massive, like a very big donation of a DDR4 memory
Hmm.
recently. There is so much DDR4 memory laying around the lab that it's like, hundreds of thousands of gigabytes, terabytes of DDR4 memory that I have laying around.
You are rich.
Well, it's DDR4, not DDR5, but.
Okay, let's keep going. Networking. I mean, I think I wanted more high-level lessons.
Yeah.
This is getting bogged down at so low level that I'm missing the forest from the trees, so to speak. Okay, let's keep reading.
Networking, Ethernet gains. Besides CPU and main memory, the only other hardware resource that all instances have is Ethernet, the network, right? Figure 4
Okay.
shows the evolution of cost-normalized network bandwidth for compute-optimized instances. In terms of absolute network bandwidth, we see an improvement from 10 gigabits per second to 600 gigabits per second. So that's a
Mm-hmm.
60x improvement. Even in cost-normalized terms, the networking bandwidth
Oh,
improved by 10x. This change stems from the introduction of network-optimized instances with the "n" suffix.
maybe not wow. We always knew that the network bandwidth is easy to increase, but
Mhm.
still very good.
The first such instance based on proprietary Nitro virtualization technology, C5N, was introduced in 2018. For non-network optimized instances such as C4, C5, C6A, the cost-normalized network bandwidth barely changed.
Okay,
On-premise
let's
comparison, let's finish that before we go to
yeah.
the graph. Looking at Ethernet network cards from Mellanox, we find that their speed has increased from 100 gigabits um, uh,
To
connect
400.
X4 in 2014 to 400 gigabits per second X7 in 2022. We cannot compare the cost normalized evolution of cloud network hardware to on-premise because we were not able to find reliable and realistic prices for data center networking hardware.
Why
Um,
not?
the, this raises the question of whether economic consideration motivated AWS to manufacture proprietary Ethernet technology, allowing them to advance the technology more quickly than on-premise alternatives. Okay, so what does Figure 4 teaches us? That's the 10x, right? But only if you go for this network optimized green instances.
Okay. And these are G is Graviton, right? Well, there is also Intel C6 in. Oh, network optimized. Okay, NVMe instance storage. This was the surprising thing, right? About SSDs. Let's read. Remote versus local storage. Most modern AWS instances do not have built-in storage, but rely on remote block devices attached through some form of network. Yeah. Uh, However, there are also instances that have built-in storage devices, which can be magnetic disks, SSDs, or NVMe SSDs. We focus on instance storage based on NVMe SSDs, which have evolved considerably over the past decade and are of particular importance for database systems due to being much faster than older storage types. NVMe capacity. The first instance family with NVMe SSDs, i3, was introduced in 2016. As of 2025, there are 36 such instance families. As Figure 6 shows, the first disruption after i3 in terms of storage capacity per dollar was the introduction of the i3 instance family in 2019, which offers up to 60 terabyte of capacity and double storage capacity per dollar. Since then, we see very little change despite the introduction of dozens of new instances with NVMe SSDs. Okay, figure 6. Mm, okay. Terabyte hours per dollar. Okay.
So figure 6.
30 terabyte to store an hour is $6. Nice. Wow. Okay. Where are we going with this? I'm getting
NVMe
frustrated.
performance, remarkably, if we
Hold
look
on.
at
I want to look at this is 3 cloud specs, the need for use case specific
and
analysis.
Cloudspecs is their tool, which we can probably skip.
Uh, no, cloud specs is what do you mean there? Okay, cloud specs code base is available on GitHub. Is this the interactive tool?
Yes,
Why are we
section
talking
3
about this?
is the
Oh
tool.
my God. Like lessons for cloud systems. Can we just skip to this? Because I'm not interested in any of these. Okay, I'll let you read, Alexei. Then
NVMe
then
performance.
let's try to get
Yeah,
to
let's try to finish section 2. That's
lessons.
where
Sure.
the things are.
Oh,
So
they have a GPU and
yeah,
accelerator section, even though
yeah.
they said they are not going to look at it.
NVMe performance, remarkably, if we look at I/O performance per dollar, we find that i3 instance introduced in 2016 is still the best instance by almost 2x. This is true both in terms of sequential read
What?
throughput and random 4 kilobyte reads.
Somebody dropped the ball really badly here. The i3 instance introduced in 2016 is still the best instance by almost 2 times. What?
I mean, again, I am not that surprised, right? Because like,
Why?
um, mm,
Like
the
field
NVMe.
is the field is going backwards. What are we talking about? This is 10 years ago.
I mean, it's all the PCI bus, right? And VME sits on a PCI bus. In 2016, probably, what was it, PCI 3? I don't know. Um, like I'm not surprised that you're not going to get that much more throughput out of it, right? Like you will get the improvement, but again, it's a normalized for cost.
But why are people then paying for more costly things than going back to
Because
the,
no one needs a 2016 CPU.
oh, this is not going to work with the current CPUs?
Well, it's an i3 instance. It's a 2016 instance, so it has
Oh, I see
2016
what you're
CPU,
saying. I see.
2016, right?
It comes, why, but why does it need to come bundled with it? This is
Because
storage.
it's
It doesn't have
no,
to come.
it's not block storage. It's not over the network. It's physically in the box, NVMe over PCI Express
Hmm.
attached to the CPU.
Hmm. Oh
Right?
boy.
The entire notion of like why NVMe is fast is because it runs over PCI Express bus, and typically the CPU will
Mm-hmm.
have some PCI E lanes going straight into the CPU, so CPU can work with it
I
directly,
see.
right?
I see.
So so
I
so
mean,
so
I can now see why people are so excited about disaggregated systems. They want to separate. They want to have the computes evolve separately from storage and use this cost-effective things as just storage nodes, maybe.
yeah,
Be-
for cost
Because
effectiveness, right?
their computes suck, so to speak. Interesting. But they are still great deal for storage. Wow.
Well, like again, like with disaggregation, right? We can separate this, but then we introduce this massive latency, right? Where
Mm-hmm.
you have
Yeah,
this
yeah.
disk attached over PCI Express to the CPU. Now you have the CPU that probably talks again via the PCI Express or whatnot to network card, right? Network
Mm,
card goes over the network, couple switches before you reach the other end, where maybe there is some DMA, right? You would hope so that goes from network card to that drive with your block or whatnot, right? So you're
mm-hmm.
adding so much more in terms of latency into this,
Mm-hmm.
right? So you know you will be paying the price. The disaggregated architectures will pay a very very expensive price
Yeah.
in terms of like latency.
Yep. What does the on-prem comparison say?
The
Stands
stagnation
in.
of SSD
Oh.
capacity since 2019 and I/O throughput since 2016 stands in stark contrast to on-premise trends. Cost-normalized NVMe capacities have increased by roughly 3x in the same time frame, and I/O throughput by over 5x. The growing gap between cloud and on-premise NVMe performance is illustrated in Figure 7, which compares the read IOPS for one NVMe device. While in 2018, AWS NVMe SSD performance was state of the art, this
Mm-hmm.
is no longer true. Since 2020,
Mm.
on-premise SSD performance doubled twice with the introduction of PCIe 4 and PCIe
Oh.
5 devices, while AWS NVMe performance has stagnated. The recently announced next-generation PCIe 6 devices um,
Alex, I don't
and
get it. Like Amazon AWS cannot adopt PCIe devices,
I mean, it has, I mean, NVMe runs over PCIe,
right?
right?
So why? So
Um,
that means Amazon is making money off this, so it's not reflecting this on-prem gains to
I don't know, man.
cloud. Hmm.
I don't know. Maybe there are some hardware limitations, right? Like as I said, like typically CPU will have some PCIe lanes that are attached directly to it,
Hmm.
but then you're virtualizing things, so you're sharing that I/O controller, right?
Mm-hmm.
So maybe that has something to do with it. Maybe the PCIe like the generations improved, right? Now you have twice as much bandwidth per lane going from let's say 4 to 5, right? But
Hmm.
maybe again you have 4 times as many cores, the same number of lanes, and now you again getting like it's all about like keeping the other resources scaling as well, right? Like if you double the throughput on your I/O, but quadruple the number of cores, and then sell that, in the virtualized environment, you may end up in a situation where you actually get the same, I/O performance per core.
Hmm.
You know what I mean?
Not really.
So imagine you had a CPU with one core and 1 unit of I/O performance,
Hmm.
right? In 10 years, that CPU became 10 cores.
Yep.
We tenfold the cores. And in the
Hmm.
same 10 years, our I/O performance, um, uh, you know, like doubled twice, right? So it went
By
from one
I/O,
to
what do you mean by I/O?
the bandwidth.
Bandwidth between CPU and memory?
CPU and yeah, like the NVMe bandwidth, right? The PCI
Okay.
bandwidth, right?
Mm-hmm.
So you had one core that became
Mm-hmm.
10, one
Okay.
unit of bandwidth that now became
Mm.
4.
Mm-hmm. Mm-hmm. Okay. Okay. But on-prem things also have more cores than before. How come they have better read IOPS compared to, and the gap is increasing compared to, oh, could this be disaggregated gap? No,
No.
they're talking about the same node. Mm,
Um, Again, the analysis here doesn't tell you much, right? What kind of on-prem are you running?
mm,
How how how
mm,
how do you virtualize it? Things like that.
mm. Okay. 2.5 GPUs and accelerator. As discussed in section 2.1, cost performance of CPUs has mostly stagnated, suggesting that hardware specialization may be economical. To investigate this, we compared the development of cost-normalized 32-bit floating-point operations over time. For GPU instances, cost performance has improved by roughly 4.7 times from the P3 to G6E families. Since 2019, AWS has also released two generations of instance types, Infantron, featuring custom-built machine learning accelerators, ASIC. As figure 8 shows, the TRN2 accelerator family has twice as many flop per second per device as the G60, blah blah blah, indicating that hardware specialization. Yeah, okay, I get this. And yeah.
Mhm. Well, here is where the software also plays like super big role,
Mm,
right? Because like if you compare things like NVIDIA GPUs and AMD GPUs, right? Especially like
mm,
older AMD GPUs. On paper, AMD GPU may have, very
I see.
comparable like
I see.
flops, right?
Yeah.
But
Yeah.
you may not be able to extract all these flops in
Yeah.
real like workloads with the software
Hmm.
that AMD has
Yeah.
compared to NVIDIA.
Yeah. Okay. Cloud comparison, AMD 16 cores, 128 gigabyte RAM. AMD. Okay. This is now we are going across cloud. Okay. Because so far it was AWS, and now comparing similar things across cloud providers to see if
Mhm.
any of them is charging too much. Okay. Oracle. What? No, I thought this was Oracle. Okay. Amazon Germany is charging more. And Oracle is. Am I reading wrong? Is this a steal? Oh, Oracle gets you, pings you from the software license prices, I think. Uh,
No, like I mean, Oracle Cloud is cheaper.
a lot cheaper.
Mhm.
But I guess they ping you from they get to you through the software
Why? If you don't
prices,
use
licenses.
Oracle, if you don't use Oracle databases,
I guess you have to use it. I don't know.
no. I created an Oracle account and just run some VMs and just the cloud,
Oh,
man.
really?
Yeah,
Okay.
just the cloud. It's
Uh,
not big, right? So they want you
mm,
to, come in.
okay. This is also like the small players, they said.
Yeah,
Look at
yeah,
this. This is like 4 times cheaper.
yeah.
This is 2x cheaper. Interesting. Okay, comparing clouds. Okay, Alex, you read.
So next, we extend our analysis to other clouds because an exhaustive comparison of cloud providers is beyond the scope of this paper. We focus on specific configuration, reference configuration available everywhere. We
Okay,
choose instances,
let's skip hyperscalers, focusing on three
three major
major.
hyperscalers,
Mm,
AWS, Google, and Azure. We see similar prices for our
yeah.
chosen configuration.
Mm-hmm.
Generally, the pricing models and offerings of three major hyperscalers are very similar to each other. For example, all three clouds have instances with NVMe storage, charge similar amounts for inter-region traffic, and offer Intel AMD and ARM CPUs. There are exceptions to these rules. For example, AWS has an edge in terms of networking speeds with its
Mm,
C7GN, C8GN instances, while
mm,
Azure doesn't charge for network traffic between availability zones of the same region.
mm-hmm,
We plan to extend Cloudspecs database with information from other clouds and leave detailed comparison of the strengths and weaknesses of future work.
mm-hmm,
Smaller clouds. The similarity of prices between the three major hyperscalers could indicate a highly competitive market where competition drives prices of basic infrastructure like common virtual machine types close to marginal cost. However, a price comparison with other clouds seems to falsify this theory. For example, Germany-based Hetzner, however you pronounce it, is almost 4 times cheaper than AWS in the US East 1 region. The gap increases to 4.7 if you compare, the German regions,
mm-hmm.
right?
Yeah.
Oracle and OVH Cloud also managed to be substantially cheaper than the big three.
Okay.
Mm,
Other factors. Admittedly, hyperscalers offer additional benefits to customers that are hard to match by smaller clouds. In particular, they offer a much larger set of specialized instances. I don't think that's a, I don't think that's a feature. I thought you were going to say better availability, or something.
more specialized services, right? The like
Yeah.
managed
Yeah. The
services. Look up,
environment. Yes.
yeah.
S3 is there for you. Furthermore, smaller clouds have fewer data centers, which can be important for geo-distributed applications, often charged by hour rather than per minute or second. Yeah, right. The smaller guys charge by hour, and that makes a difference, definitely. On the other hand, that's a big thing. The three hyperscalers charge extremely high prices for moving data out of their cloud, of course. For example, even ignoring Hetzner's 20 terabyte per month free traffic, per instance, AWS charges 50 times more for egress per byte than Hetzner. Okay,
So
yeah,
once you're in AWS,
yeah.
you're there forever.
Data, storage cost is so cheap, you keep putting the data, but then you won't be
Yeah.
able to get it out. Except with a truck, maybe with a truck. Amazon has that
Oh,
service, I think.
they will charge you a lot for the truck as well.
Really? Okay.
Of course.
Mhm. Okay, this is the tool. Mm, Let's skip the tool.
Yeah.
Oh, through the looking glass, Cloudspecs. Okay, I get it now. I get the
Yeah.
through the looking glass thing because they called it the Cloudspecs, and okay, sort of relevant. Related work, economics for the cloud, Jim Gray's 5-minute rule, recently revisited in the context of caching, yes, last year's thing, research efforts, blah, blah, blah. Okay. Lessons for cloud systems. Why don't you read, Aleksey?
Okay, so several lessons here, right? Gains from specialization. Cloud hardware is becoming more diverse, which makes instance selection more difficult, but also leads to large opportunities. Selecting an instance optimized for a particular resource, bottlenecks such as CAGN for networking over a more generic one such as CAG can improve performance by 5x. This assumes that the software is capable of exploiting all hardware resources. Scale-up opportunities, although the
What
cloud...
this assumes that, oh, this assumes, okay.
Scale-up opportunities. Although the cloud is strongly associated with distributed systems, it also enables another form of specialization, extreme scale-up. In AWS, instances with 448 cores, 32 terabytes of RAM, 128 terabytes of NVMe storage, and 600 gigabits network bandwidth are available. The availability of such large instances also makes it possible to design large single-node systems. 120 terabytes of NVMe storage sounds already old. Kioxia, like last year, I think released a 245 terabyte SSD.
Oh my God. What are you gonna store? Jeez. And yeah. Okay, we got rid of the Bitcoin mining thing, but now there is AI. And what are these large single node systems? Okay, ARM's taking over. In comparison with prior decades, x86 CPU performance per dollar has stagnated. The biggest compute cost improvements come from the introduction of Graviton instances. Within a handful of years, ARM instances went from being an obscure niche option to the default choice. Today, Graviton-based instances are not only the best choice in terms of compute, but also network bandwidth, main memory capacity, and NVMe capacity. Similar trends can be observed in other clouds as well. It currently seems like developers should seriously consider porting their systems to ARM. However, the jury is still out on the long-term impact of CPU vendor diversity and prices. Okay. I mean, I think Graviton gives you a lot of benefits in terms of energy efficiency as well. They don't talk about this, right? They have been saying Graviton is great for this, that, but from what I know, Amazon is more excited about Graviton because it uses less power, and this doesn't take that into account.
Well, it does in a sense, right? Because it's a cost efficiency, Murat. So less power, that means that Amazon can run it for cheaper, right? And maybe
And
pass
offer
on
it for cheaper,
and
yeah.
offer it for cheaper.
Yeah.
And it's not just power, right? Like if you run it with less power, it means you need to cool it less, right?
Yeah,
So it's not just
exactly.
like the power that the actual like chip consumes.
Right.
Yeah.
Yeah. Okay. Memory and NVMe is your thing, and
Memory and
networking is your
NVMe.
thing.
Main memory prices have largely stagnated, and since 2016. Data-intensive applications can resort to NVMe, which was the major disruption in the storage space in the past decade. Of course, NVMe SSDs have very different characteristics from DRAM, potentially requiring major architectural changes.
Okay.
Network bandwidth explosion, by far the largest gain in cost normalized terms over the past decade was the networking, which improved by one order of magnitude. We already saw that.
Yeah.
Given the relative stagnation of other hardware resources, this challenges the traditional assumption that network bandwidth is the bottleneck in distributed systems and can have major architectural implications. For example, the AWS Aurora OLTP architecture was specifically designed to minimize network traffic, which raises the question of whether today's hardware landscape would favor other designs. That's an interesting point.
No, what's the point? Say this again.
Aurora
Yeah.
architecture is designed to minimize traffic
Yeah.
bandwidth, right? But bandwidth is the one resource that actually gets them cheaper. As CPUs,
Yeah, okay. Yeah, that's fun. Uh,
as CPU speed stagnates and network bandwidth increases, the CPU cycle budget per network packet continues to decline. Um, yeah,
uh,
I'm not entirely sure that this is correct. They haven't done the analysis, and I think it may not be correct here.
I don't know, the Aurora thing, right? So it minimizes network traffic. Fine. They are saying network traffic is cheap anyways. But maybe by minimizing network traffic, they are still advantages at the end of the day
Yeah.
because they are more efficient compute and less costly.
Mm.
Okay.
Fully exploiting this resource may require
Right,
majors.
because we had also seen from the previous paper that like network traffic is takes a big toll on the CPU as
Yeah,
well.
yeah.
And you don't want that. So this is like, yeah.
Yeah.
Okay, everything is connected.
NVMe performance stagnation. Broadly, most of the hardware trends in the cloud follow similar developments as the general server hardware market. One major exception is stagnation of NVMe performance. I think
Yeah.
they repeats in everything that they said. So like I'm
Yeah,
not
yeah, they
seeing
are.
any
They are.
deep analysis here.
Okay,
Um,
for example, cloud-native warehouses such as Snowflake use NVMe as caches, but given fast networks, it may be more economical to directly read from S3. Yeah, I think we are seeing more and more of this trend with disaggregated, uh, basically disaggregated systems try to read directly from S3 rather than deal with NVMe. Right,
uh,
so they read from page servers from RAM as well as
eh,
go to S3 for durability and also snapshots. Yeah, I mean for an analytical solution, it may not be a bad idea to read from S3. Not it's not OLTP, it's OLAP.
so um, the cost of S3, right?
Mhm.
They do charge per request,
Yeah.
right? So quick Google tells me uh, S3 table put request prices $0.005, so half a cent per thousand requests,
Mm.
right? I wonder what's the read is. I mean, the page is complicated. But my point is, if you're like pegging S3 a lot, you may be just paying a lot of S3 prices. So that's why you want to like
Mm.
NVMe, you pay it once and it's there.
Mm.
Right? You can read a million times from that NVMe drive for the same,
Mm.
static price. S3 price is not static.
Yeah, okay, Alexa, but they are citing papers. Do you have papers to cite? They say nine. Okay, that's another Viktor Leis paper, 2023, exploiting cloud object storage for high performance analytics. They thought about this. They are
I
not
am
just
citing,
making it
Murat, I'm
up.
citing you the AWS pricing page.
You didn't do the math. They did. See, the other 23 is also his paper,
Yeah.
and it's saying BTR blocks, efficient columnar compression for data lakes. Victor Leis had been publishing hardware accelerator. Given the stagnation of CPU speeds, specialized accelerator. We are repeating everything. You are right.
This
Multi-cloud
is something that I notice a lot in papers, Susan.
Yep, yep. This is becoming a nuisance in recent
Uh,
papers. Everything is repeated 3 times.
I'm wondering if this is like really how people write, or it's just an artifact of LLMs.
Okay, multi-cloud opportunity. Again, repeat. Like we
Or,
did
or, or
really.
maybe if you repeat it 3 times in a paper, then LLM reviewer is going to like finally understand the point you're trying to make.
I don't know. Okay, feature work, Cloudspecs and interactive approach. Ah, give me sliders, man. I don't want to write the SQL query. Give me sliders. That's feature work. Uh, interactive data sharing. I mean, these guys are data core database guys, and so they're like, oh, SQL. What else do you need? Interactive data sharing. We believe that Cloudspecs framework is also useful for other use cases. What? Size set function. Okay, shilling the Cloudspecs thing, fine. Database benchmarks. Uh, okay, multi-cloud. Feature work is also repeating the same things. Okay, we did it. We did it in less than 1.5 hours. And I am overwhelmed with all these alphabet soup, and I would have liked high-level takeaways and what would it mean for me as a system designer. I would have wanted to take that from this paper rather than how this was um, done, the low-level things. The NVMe thing is interesting, but I guess we have to interpret it. Uh, yeah.
Yeah, you want to stop recording or we're gonna talk?
Yeah, let's
Okay.
let's stop recording and talk. Yeah, but okay, before we stop recording, what did we flag here? Okay. NVMe storage performance has stagnated. Okay. Network bandwidth improved. We knew CPU and DRAM gains are much smaller, but they are there. Cores keep increasing, but we are not able to keep up with the increasing cores. Something is giving up, probably both from hardware and software sides.
Mm. I mean, their argument is cores are increasing, but the price is like not
Yeah.
decreasing fast enough, right? Or like the price per core,
Yeah. Performance
yeah,
per dollar.
yeah, performance
As
per
they say.
dollar, like cores 10x, performance per dollar 2x, right?
Yeah. Okay,
But
let's
again,
stop
like it
recording.
does make sense in
Hmm.
some sense to me, right? Because the modern CPUs, they run harder, they use more energy, right? They are more expensive to manufacture. Um, and who knows? Maybe they don't even leave us long, right? Like the CPU in my workstation died after 2 years.
Yeah. Yeah. Hmm. Hmm. Okay, that was AMD, right? AMD
Hmm.
owes you CPU. Okay, Aleksey, give me the dirt.
You still recorded.
Oh, I'm still recording. Hold,
I mean, I will truncate
hold
it
on,
anyway,
hold
but
on. Yeah. Uh, I don't stop recording. Okay.